All right, so we get to the early 1800s and we get Dalton. John Dalton, I find him an interesting guy because he does this work all in like atoms and stuff. And so I think of him as like a physical chemist. It turns out he was also colorblind and he didn't realize this until real late in his life. He went and he was buying some socks for his mother as a present. And he couldn't really see the color red. So he thought he had bought her some, very prim and proper nice black socks, and it turned out they were bright red, and her mom was shocked and appalled that he would give her such tawdry socks. So he discovered he could not see the color red, and he thought maybe his eyes didn't filter that light, so he wanted people to save his eyeballs after he died and see if they could shine light through it and see that like red wasn't getting through. And of course it turned out that's not at all what was happening, but that was his theory to his color blindness. But that had nothing to do with atomic theory. So let's go back to atomic theory. So he's taking all of these observations and looking at the way people are normally thinking about matter. Normally they think about matter like mashed potatoes, and I can just keep cutting it in half forever and ever down to the tiniest little bit. And I'm never going to get to that smallest individual piece that's the ultimate unit of a mashed potato. I can just keep cutting it down, right? So we call that continuous model of matter. The idea was that even beyond what we could see, that there would never be an end to how much we could cut it down. And so that was before the idea of atoms. And that was what was commonly thought of up to about 1800. Dalton starts looking at these laws and he says, you can't really explain, particularly compounds, if we have this continuous model. There's no reason we would always get those exact ratios if the amount of matter could be any size. So he draws on an ancient Greek idea of atoms, that Democritus came up with this idea that was atoms exist and that was the only relationship to it. Like everything else he said about atoms was completely different. So we're not even going to talk about Democritus. So first he defined them. He says atoms make up everything. Everything that you touch and see and all the chemical reactions, that's atoms. Everything has atoms. And they are indivisible, which means they're just like one thing. There are no parts to them. And from his perspective, God created them when he created the universe. And at that point, they started existing. They have always existed. They will exist through eternity. And there will never be any more atoms. There were never any fewer atoms. Atoms always existed exactly as they are. They cannot be created or destroyed. So he's defined his atoms. But now he has to explain the stuff that we've observed. So not everything is identical. So how do we make different stuff? And that comes down to elements. What are elements? Atoms of one element are going to have one mass, and atoms of another element are going to have another mass. So all hydrogen atoms will weigh 1, and all carbon atoms will weigh 12, and all oxygen atoms will weigh 16. And that's how you tell the difference. This is Dalton's view. Now we're going to notice some things in here that don't quite jive with our understanding. So unlike a law, this is more like a model. A model is something we use to help understand, even if we know there are problems with this. So this is a great way to explain atoms to like a 10-year-old who maybe aren't going to get all the gist of the subatomic particles and nuclear reactions and things like that, okay? But it has problems that we know about. We'll talk about that after we talk about these parts. Okay, so he tells us how elements are different, and he says we can't switch from one to another. Because if we switched from one to another, it would have to change what its mass was. All right, so now we're going to start drawing in the laws. So first he's going to talk about the law of definite or constant proportions. He's talking about compounds, and that's in that law. And he's talking about ratios. And so that's proportions. So he says compounds result from a combination of specific numbers of atoms of those elements, which means, for example, every water molecule will have 1 oxygen, every water molecule will have 2 hydrogens. Okay, so this really kind of establishes the idea of the molecule makes the compound. And that ties directly to the law of constant proportion. So on your quiz, I might give you these bullet points as your choices, A, B, C, D, and say which of these explains why we have that law of constant proportions. Okay, so something to remember is that the law of constant proportions is tied to this one about the compounds being in specific ratios, having specific numbers. I am never going to say write out all the parts of Dalton's theory. So don't spend your time memorizing these different parts. Understand what the parts mean, but you don't have to repeat them back to me. All right, so the last part is going to pull in our law of conservation of mass. So if all the atoms have always existed and we can't change from one atom to another, then what's going on in chemistry? When we have a chemical reaction, instead of creating or destroying anything or changing the atoms, what we're doing is rearranging the atoms. So we think of that as breaking bonds, breaking apart the molecules, forming bonds, making new molecules. So the atoms can't be created or destroyed. This is why we have conservation of mass, because we can't create mass or destroy mass. We're just changing them around. We're changing what's attached to what. So Dalton first published this in about 1803. I think we were probably on our second or third president at this point. So very, very early in American history. Dalton's over in England, though. But it takes him a while. He revises it a few times, keeps publishing it. It takes him a while to convince the scientific community that atoms exist and this is how matter works. It takes a while to change prevalent thought. So several decades. Around this same time, if we think back to Benjamin Franklin flying his kite, that would have been in the early American history. He's flying his kite and he gets zapped with the lightning and then they have the electricity. Well, in the early 1800s, a lot of scientists were like, well, how can we control electricity? So they developed the first batteries by using different chemicals and combinations. And they were like zapping everything. They were like, what happens if we run electricity through salt? Well, you get sodium. So sodium and potassium were discovered in the 1800s because they were like, what can we do with electricity? They were also doing things like, what if we zap a dead frog? Oh my gosh, its leg moves. And then somebody writes a book that's like, what if we take human parts, sew them together, and zap it with electricity? Why, we get a monster. So Frankenstein was actually written in response to this obsession with electricity and making things move. And this idea of, can we make something come alive? Can electricity be harnessed to play God? So all through the 1800s, people playing with electricity. Meantime, they're figuring out atoms. And they're like, okay, we know what atoms are. Which things qualify as elements and what are not elements? So they're like, can we purify it down? Can we not purify it down? Okay, sodium's definitely a thing. Brass we can separate. So that's going to be two things. So we got copper, we got zinc. So they figure all those out. By 1869, we have what most resembles our current periodic table being published for the first time. So Mendeleev is given credit. Another person by the name of Michelson came up with it roughly the same time, but Mendeleev published first, so he gets the credit. So we got the periodic table, we got the elements, and we've got cathode ray tubes. So this is one of the new toys. So think about like, oh, here's this new thing that does this fun thing that's the new toy on the market, but like it's not, doesn't have a purpose, but it's fun to play with. So a lot of scientists were playing with this. This is an example of it here. Hold this up. Apparently pull off the things. And so you're going to be able to see a little bit of light, but this is kind of small. So I'm going to show you a picture of it that you'll be able to see the parts a little bit better. All right, so this tube is evacuated, so it doesn't have air in it, but it's got electrodes at either end. And so we've got electricity running through it that is causing some light to occur. So you might be able to see like a little pink glow here, and then there's like a paddle wheel that has some green lights on it. So the pink glow is what they were calling the cathode ray. So the thinking at the time was, well, maybe this is a new element that we've just discovered. Maybe it's a form of energy. What's going on here? I am not big on memorizing names and dates, but you really ought to know that Dalton is associated with the atomic model and that J.J. Thomson is associated with the cathode ray tube. Okay, so this one kind of goes out at the end. What they thought was really cool about this is they were also discovering things that glowed. Scientists love stuff that glow. And so they coated this with something like zinc sulfide. And if you hit it with these cathode rays, it lights up. And so they have a cathode, a little piece of metal here, an anode here. This looks like a coin, but it's got a hole in the middle. Okay. And then they would run electricity through a battery. So the battery would pull the electrons off of the anode, so that becomes positive, and put the electrons on the cathode, so that becomes negative. And then the ray would be created when the negative charges that would build up on the cathode would fly towards the anode. Okay. And so most of them would smack into the anode and neutralize, but some of them would fly through that hole in the middle. So if it flew through the hole in the middle, you could get it to hit this wall and glow. And if you made the hole a little bigger, you can make a bigger glowing spot. And they would, have little devices that they could put in there. Like they might have like a shape of a cross. And so they have it glow, but there'd be a shadow of the cross. We used to have a cathode ray that was like that. And so mostly people were just playing with it. Like, isn't this a cool thing? Thomson was like, but what's going on? So one thing that he noticed was that if you take a magnet where this pink glowy thing is going, you can get it to move around. And that means that it's charged. So at the time they understood that magnetism and electricity work together. So magnetic field causes bending. That means it's charged. So one thing I might ask you about this is, how did he know that the cathode ray had charged particles? Well, it bends in a magnet. He also noticed that we were going from negative to positive. So whatever this cathode ray is, it has to be negatively charged because it's attracted to the positive. And then the other thing he did, which really made him unique from other people, was he started replacing this cathode and said, well, what if it's gold? What if it's copper? What if it's aluminum? What if it's zinc? What happens in each of these cases if I run the electricity through it? And the answer was the same thing, exactly the same thing. It wasn't a property of the given element. It was something that was the same for every element he tried. Now, he can't try every element in existence, but all the ones he tried were the same. So he said, well, it must be a part of those elements, a part of those atoms. So what thing is a part of all atoms and negatively charged? Electrons. So he gets credit for discovering an electron. All right, so his idea was we don't just have a solid ball, we have a ball that's positively charged, but we have these little beads in it that are negatively charged. So they couldn't get anything positive to come off at the top. So they thought, well, most of it is just this big mass that has a positive charge. And then there are these little things that can come off. And this kind of looks like raisin bread or a British dessert called plum pudding. So this is called the plum pudding model of the atom. So we wanted to know, what is that charge? Millikan did his oil drop experiment to discover what the charge was. So they didn't know, like, is it the same for every electron? Are there big electrons and little electrons? Can I have any range? Like, is it analog? Like, it could be anywhere in between, or does it have to be certain things? So to describe what you're seeing here, this is like a perfume bottle. It's called an atomizer, and it's going to spritz just a tiny little bit of oil in tiny, tiny misty droplets. And they're going to drift down. And as they drift down, they're going to hit this plate. Most of them are going to stop, but there's a hole, and some of them are going to go through the hole. As they go through the hole, this is going to shoot X-rays at them. Okay, and those X-rays are going to cause some of them to become negatively charged, to get electrons attached to them. And so this plate here that most of the oil is collecting on top of, it's gonna be charged with a battery to be positive, and the bottom's gonna be charged to be negative. So as this electron thing is drifting down, it's gonna get near that negative plate and it's gonna repel and be attracted back up towards this. So by adjusting how much charge was on those plates, they could tell what the charge of the electron was. How much did it take to get it to stay exactly in the middle? And so they were able to do that. This is a guy looking through like a microscope. So this is a face here. I know from back there, just kind of looks weird. Blob. And so the main thing that he discovered was that he didn't always get the same number, but he got multiples of the same number. So he was measuring in coulombs and he got 16 and he got 64 and he got 32. So it was always multiples of 16. And so he said, well, probably the charge is 16. And when I'm getting 32, I just have 2 electrons on the same oil droplets. And when I get 64, I have 4 electrons on the same oil droplets. That's how we get the charge. I'm not really going to ask you too much about Millikan. So you should know that he found the charge, oil drop experiment, but we're not going to go into how he knew different things. This one is the important one, Rutherford. So Rutherford was playing with the new electricity. By the end of the 1800s, they'd been playing with electricity for a while. They had done all of the cool stuff. They had made things glow. And then they found some things that like kind of like glow in the dark stickers. You put them out in the sunlight or you put them up next to a flame and then you run into the bathroom where it's dark and they glow. If you ever did that with stickers when you were a kid, like they discovered the compounds that do this. And there was some guy that comes along and he'd been rock hunting the same day and he put his rocks in the same drawer where he had these glowy materials that would only glow if there was light around. You know, if you wait long enough, it stops glowing, and that's, I gotta run back out and put it on the sun. But he pulls them out of the drawer, and they'd been in this dark drawer, but they were glowing. And so this compound, this rock, was making them glow. And so there's probably uranium in there, which is radioactive. So from there, different elements were discovered that kind of caused this phenomenon, and radioactivity became the new electricity. Like everybody's studying radioactivity. Marie Curie's discovering different compounds. She's getting her Nobel Prize. Well, Rutherford's discovering the different particles that come off. And so he names them. He says the big one is alpha, and then there's a smaller one that's beta, and an even smaller one that's gamma. So we're going to focus on alpha. What does he know about alpha? The alpha particle is very dense and small. So think of it like a bullet, but it has a positive charge to it. So that's what he knows about it. And he wants to see, well, what can it do? So he knows one thing is that when it flies off of things like uranium, like you can stop it with certain things, but like a thin sheet of paper, it's just going to fly through. So he's trying different thicknesses and different materials to see what will go through. So his idea is we're going to shoot the alpha particles, positive charge, positive little bullets, across here. We're going to have nothing in the middle, and we're going to count how many little glowing lights we get, showing us that they're hitting over there. And then I'm going to stick something in the middle, in this case, gold foil, and see how well that blocks it. Do we get the same number? Do we get fewer? And being a PhD who is all full of himself and just knows the best of everything, he wants to spend his time having tea and smoking and telling people how great he is. So he tells his students to do his work. So one of his students is named Geiger, and Geiger's job is to run this experiment and count how many times he sees the glowing here. Okay, so if you've heard of a Geiger counter, that's something that's used to measure levels of radiation. The Geiger counter is named after this guy whose literal job was to count how many times this lit up. But what he noticed was that sometimes, not very often, 1 in 1,000 times, we might have a little speck here, a little speck there, things glowing off to the side. And every once in a great while, one every 10,000 times, there might be one that goes backwards. So Rutherford was like, I was as shocked as if I fired a cannonball at a sheep and that cannonball bounced back at me. Now, if you fired a cannonball at a wall and it bounced back, that wouldn't be too surprising. but a sheet on the clothesline, you're not expecting that. So he was thinking with this plum pudding model here, with everything spread out, that the alpha particles would just go straight through. And since it's the same all the way through, there's no reason that one part of it would stop it and another part wouldn't. So it should all behave the same. But it wasn't behaving that way. So he tells Geiger, you did it wrong. Because he's not going to believe Geiger. He's just a student. So Geiger does it again. He says, do it again. He does it again. He checks it himself. He runs the experiment himself. He said, by golly, you're right. And Geiger's like, I know, I told you. So now he has to explain it. So he comes up with another particle. So Thomson came up with the electron. And what he says is what's going on here is these alpha particles are hitting a part of the atom. Now, 3 things I know about this. I know that most of the time the particles are not affected by it. Okay, so this is like a 1 in 10,000 times this is happening. So whatever it is that's affecting it has to be teeny tiny, because most of the time I'm not close enough for it to matter. Okay, so first observation is that it is small because it doesn't happen very often. The second thing is if we have things that are bouncing back, it's got to be pretty dense, pretty heavy for that particle to hit it and bounce back. Okay, so remember, we're thinking of this as a bullet. For the bullet to bounce back, whatever it's hitting has to be pretty dense for it to be able to come back. Okay, so whatever it is dense and it's very small. And then he also knows the alpha particles are positively charged. So what happens when I get 2 positive charges near each other? They go apart. So he says, if I'm getting close, so here's the alpha particle bouncing back. If I'm getting close, but I'm not hitting it, it's going to kind of go to the side. There's a deflection. Okay, so that deflection is just when they're close, but not actually hitting. So what is a really dense, really small, positively charged part of the atom? The nucleus, right? Or proton are in the nucleus. At that point, he hadn't discovered protons, but he discovered the nucleus, right? Okay, so we need to know Rutherford had the gold foil experiment, the 3 parts of the discovery. It's dense, it's small, and it's positively charged. And then how we know those things. And so we move from the plum pudding model to this idea. All that positive charge is in the middle, and the electrons are on the outside. So Rutherford's ideas, they're just on the outside. He didn't really explain it. Later on in the semester, we'll talk about Bohr, who says, no, there's got to be some better explanation for what's going on there. And some other scientists come up with protons and neutrons. We won't go into those. 2 experiments you really need to be able to talk about: Thomson's cathode ray, Rutherford's gold foil. And how do we know what we know? What was the line of reasoning that led to this is an electron, this is the nucleus? All right. So that's where I'm going to stop. Any questions? All right. Have a good weekend. Don't forget that you have vocabulary due. And I will see you Wednesday.